Okay, so today we are looking at the distribution mode 1, some means of arithmetical functions, and people who are involved in that are Florian Luca, Enrique Vagnez, Mehdi Hassani, and Mohamed Naziri Zareh. Mehdi Hassani is a former student of mine, he's lecturer in Zanjan University, and Mohamed Naziri Zareh is a joint student of ours, so it is the situation where he is both my son and my grandson. So in usual life it is a bit curious, this type of thing. It's not recommended, but for mathematics it's okay. So maybe some definition. We talked in May. We talked about this question of distribution mode 1. I just want to say a few things for people who don't remember it or who are not there. So some basic definitions. Okay, so you have UN is a sequence of real numbers, and then today there is no temptation to look outside. Usually nice, but okay, sorry. So we say that UN is dense modulo 1 if you have the following, that when you take all the fractional part of UN, so you take this set, n belongs to n, and so it is a subset of 0, 1, and when you take the closure of that, or the usual topology, this is 0, 1. If you want to see them as element in 0, 1, if you prefer to see them as an element on the torus, then the closure is the full torus, as you like to do that. And one way to see that is to say that for A and B, for all A and B with 0 less than A, less than B, less than 1, so to say any kind of interval like that, then there exists infinitely many. If there exists one for all, then there exists infinitely many, so it doesn't bring much, and such that UN lies in the interval AB. Okay, so you see that if there is one, there are infinitely many, because you can make in AB infinitely many, enumerable of course, but infinitely many subintervals which have positive length, and in which each of them there will be one element, and so there are infinitely many in that element. So okay, so this is one way to see it, and so this is density, and uniform distribution, you say that UN is uniformly distributed modulo 1 UD1, we're going to write it, uniformly distributed modulo 1 if the proportion of elements which fall into this interval is B minus A. What you expect, it is well distributed in all the intervals. So if you have the following, that you take the number of n up to x, or n, capital N, such that UN fractional part lies in the interval A, B, and what you are asking is that this is tending to B minus A when n tends to infinity. Okay? And we mentioned something in May, which is Weil's criterion, 1916, which tells you that un is uniformly distributed mod 1 if and only if for any integer k, positive integer k, you have the following 1 over n. We look at a multi-dimensional version of that possibly tomorrow, but today we don't need it. Exponential, maybe let me write it, exponential 2 pi I k un tends to 0 as n tends to infinity. Okay? Essentially, if you have good distribution like that, it means that if you are taking the, how to say, the interval, the indicator function of this interval, then when you are integrating or summing the value of that, it's exactly counting this number, it tends to this, and then it means that for any nice function, this, if you are summing the f of n of f of un for elements, then you go to the mean value, and of course the mean value of this should be 0. This is fine, and the other way around is to say that essentially with Fourier transform you get almost everything you wish. You would like to have all the k, but if k is negative, this is just the conjugate because un is real. So this means that you have it for all the rational integers which are different from 0. And of course for 0, what you have is just something which will be n. It tends to 1, and this doesn't give you any information. Okay? Good. So for example, if you take the sequence alpha n, alpha does not belong to, is irrational, and alpha does not belong to Q, then you have that alpha n is uniformly distributed mod 1. This is, by the way, equivalent. Okay? Good. Now we go into the real business. It's fine? Okay, good. I haven't looked at what has been taken. Maybe it is better to close that for having something better here. Okay. Well, so okay, let us go to, after 0 it's 1. Okay, introduction. Sorry?
You said something to close.
No, I said this is closed because maybe it is better to see what is on the board. Yeah. Okay, so there is something which was introduced by Florian Luca, Luca's mean, and in a conference in 2007, Lucas considered the following things. He considered the arithmetic. Sorry? Luca's mean. I mean, Florian Luca is Luca with no S. My son is with an S. Yes, but it is a first name, but there is also Edward Luca, Luca number and Luca sequences and things like that. No, this is Florian Luca. Okay, so it's correct to put it that way. Okay, so the question that was raised by Florian Luca is to say he is considering the summation, the mean value of phi of m. Phi of m is essentially 1, you see, on average. And so this sequence is something which is about linear. And no, phi of m is m. Phi of m over m is constant. Okay, this is something like that. And he was also looking at the geometric mean, which is just the product when m is up to n of phi of m. And then he was taking the power 1 over n. Okay, this is the geometric mean. So those two sequences have a linear growth. This is equivalent to, should I give it to you? Yeah, 3 over pi square n, and it is rather good approximation, but it's not plus little o of 1. This plus big O of log n. We'll see a lot of summation like this one, so there's no point to say anything about it right now. And this one is equivalent to E times 1 over E times the product when P is larger than 2 of 1 minus 1 over P to the power 1 over P times n plus something which is again a big O of log n. Okay. By the way, this you get from the following. You remember that there are phi of m. Again, we can write it in different means. It is m times the product when p divides m of 1 minus 1 over p. This is one way to see it. And it is also the summation when m. This is summation. I'm going to say something stupid now. This is also m times the summation when d divides m of mu d over d. Just expanding this product. Okay? So, of course, if you are looking at this one, it's better to take the summation because then you can just reverse the summation. And if you are looking at the product, it's better to start with the product here. So you understand that what you have here is something which is m times something to the power 1 over n. So it is n factorial times to power 1 over n, and this is why you get n times 1 over e. And as regards the product there, you have the product, and you see how many times a prime will occur. It will occur something like n over p, but you are taking it to power 1 over n, and this is why you have 1 over p. So this is not difficult to get those things. So let us go now to the Lucas question. So Lucas question, and of course we're going to talk about variation on that. Lucas question was are the sequence an, gn uniformly distributed mod 1. Okay? And then it turns out that, when Luca was presenting that in that conference, Schinzel was here and said, at least if you cannot say that it is uniformly distributed mod 1, can you say whether it is dense modulo 1? Schinzel asked, is it dense? Okay. So, and then when Florian was explaining that at the conference in Marseille, a uniform distribution, just in January 2008 or something like that, I had some idea something could be done, and we discussed that. And for me, it's an interesting question because it is the quickest paper I had, thanks to Florian. I must say that, so we discussed that on the same day. The next day, Florian was coming with the paper that was written. We looked at that for a few minutes, and then it was sent. It was accepted within something like 2-3 weeks, and it was published another 2-3 weeks later. Never had such a quick paper. So, okay, I hope everybody will have this nice experience. Possibly one thing is just to go and work with Florian. Yes, it's maybe the right things to do. Okay. So, okay, I would like to give some generalization. There are zillions of generalization. This is why I want also to present that and things which are not really well known and well understood. This is just a few generalization. You may invent everything you wish. So one thing is other means. For example, you have the square means. Sn is the square root of the summation of phi of m and up to n. Could work the same way. You have something which turns out to be trivial, which is the harmonic means, which is n divided by summation when m is less than n of 1 over phi of m. Turns out that this one is quite easy to manage. And for me, the one I like much, and I will essentially talk of this one, is something which is a bit different, but a bit nicer. I will explain you why. It's not exactly the mean, but you take just the summation of phi of m over m, and again, this is equivalent to 6 over pi square n plus another term which is log n. So okay, you may imagine everything you wish. Other functions. This is quite interesting because, so essentially we are dealing with multiplicative functions. So this, for phi of n, you can extend it to m times the product p divides m of 1 minus nu over p, or nu is a constant, or nu p over p when nu p has a nice behavior or things of this kind. This is one of the things, but all that is strongly multiplicative. At least this part is strongly multiplicative. Strongly multiplicative means that the value at p to the alpha is the same as the value at p. Okay, for a strongly multiplicative. But if you consider something, so this will be phi of m over m, and then with this part, but you can consider also sigma of m, and non-strongly multiplicative function. Sigma of m over m is not strongly multiplicative. Okay, sigma m is the sum of the divisor, the sum of the divisor of m. Okay, it's something like phi of m over m. So you have all these functions. Sorry? Sn? No, this is fine because you see phi of m is something like m. When you sum it to n, you have something which is n square. And when you take the square root, so it is linear also. You see, this is what this is something. You see, this is 3 over pi square n square. This, you get it linear by taking the mean value, and then you either you divide by n or you divide something here inside by m. It's by how to say, by summing by part. It's more or less the same kind of thing. Now, what is interesting is that we have really no idea what should be a nice set of functions. So we have some set of functions because the proof works in the same way, but we have no set of functions for which this should be true or not, when it is uniformly distributed or not, or when it is dense or not. We have no, especially when it is not. I will give you some example, but when it is not uniformly distributed, we may have some idea, but when it is not dense, we have really no idea. This is difficult to find something which is not dense. So other functions, and also means over subsequences. So you have polynomial sequences, for example, and for that it's much nicer to take this one, because if you take a polynomial value, then you will get something which is of higher degree here in n, and so you have, it starts to be a bit artificial. What is interesting is that whatever the sequence you take, phi of m over m is something which will be almost constant. So for Bn, it's really the most interesting. So what you may look at is, for example, summation m up to n of phi of g of m over g of m, g a polynomial, So we know that it is dense. This is done with Mohammed. We know something about phi, one special polynomial, phi of m square plus 1 over m square plus 1. So this sequence is uniformly distributed mod 1. This is due to Henrik and I. So this was Mohammed Naziri Zare and I. Essentially looked a lot at this kind of things, and even it can be some very highly some exponential function, but of course with good arithmetic property. You need to have some arithmetics in it, and for example, this is summation of phi over phi of f of m, where f of m is the Fibonacci number. So this is highly increasing, but of course if you take phi of m divided by m by fm, this is always something more or less a constant. And for the density, and this was done by Florian Luca and I, and something shifted primes should be quite hard. You'll see where the type of proof we have, and you understand why it may be difficult for shifted primes. We have to know something of the behavior of consecutive primes. And consecutive primes, shifted consecutive primes, this is very difficult to understand. So this I can offer it you, but I think it's hard. Okay. Okay, something that you can maybe do is to look at MUN, yes, NUN. So the summation blah 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 m up to n. If UN, well, you understand that it is positive or zero, otherwise it makes no sense. It would be complicated. No, sorry. When UM is automatic sequence. This should be doable. And it should be doable if you start with something which is, we will talk about that tomorrow, some nice automatic sequences which we call synchronizing automatic. But maybe for all automatic sequence, this should be something to look at. Not looked at to now. This is one. So you can imagine. You see you have a infinite field to think of new question about this kind of thing. Okay. So now we have to start to do something. We start with density. You see, for uniform distribution, we don't have much. We have uniform distribution for the initial things. I will tell you a word about that, and for m squared plus 1, yeah? Yeah, for m squared plus 1, but for the other one, usually we don't have it, okay?
If UM is just a binary recurrent sequence, whether it's no?
Sorry?
If for the UM, the last question, if UM is just a binary recurrent sequences, we consider
binary
recurrent sequences.
Yes, you are thinking of something like a Fibonacci number. Yes, you can. You have for Lucas sequences, but then in the sense of Lucas with the S. Yes. Yes, you can do that for sequences of the same kind. So no doubt. So let us start with density mod 1. Okay, so density modulo 1, essentially we are rather poor. We have only one method. You see, it's quite difficult to know what is going on when you are far away from different values which are far away one from the other. But if you are thinking of this, and this is now the one which I am interested in, then you know that you are going step by step or something like that. So if you can say that all the values you have, consecutive values, are rather small, then possibly you can show that it is dense. So this is the only thing we know. And we are back, here we are really in the topic of, you see, local distribution of the value. So we'll look at local distribution of function phi of m over m, either over all the integers or over subset of the integers. Okay, so essentially we have one, we know essentially one method, essentially only one method. If you find some other method, this would be really nice, because then you can prove something surely different for more sequences. Essentially one method. There are variants. If you want to apply it, you will understand that it is clear, but it is also the same one if you are looking at an, when an was the mean value, the geometric mean value. All those things will go in the same way as in the initial paper with Ferry and Luca. So let me write it as a lemma. You'll see that it is quite easy. Let un should say once for all that a sequence be a sequence of non-negative real numbers such that for any epsilon positive there exists n for which nh such that for any h in 1h, then you ask that phi u of n plus h is less than epsilon and summation h1 to capital H of u of n plus h is larger than 1, then the sum of m up to n is dense mod 1. I'll let you think 30 seconds to that and you understand how it goes. I shouldn't write too low, no? Conclusion is that it works. Okay. No, so what I am saying is the following. I look at it mod 1. I look at it mod 1. I say, okay, at some place, I don't know where, here, I have summation n is up to n of un. Now, to go to the next one, I just have to add un plus 1. So here will be the difference, un plus 1, un plus 1. And this will be the next step, because this will be the sum when m is up to n plus 1 of un. Now what I say that this one is small, so that this one can be small. Find some epsilon positive, okay, it's small. And then all that is small, all of them are small, but at least when I add all of them up to capital H, the sum is at least 1, which means that I go back here. So this means that if I take any interval which has a length which is larger than epsilon, there is an element in it. Okay? And this is true for all epsilon, and so this is true, so this is fine. In some way, this is rather trivial, and this is the only way of attack we know. You see, it's very complicated to know what is this sum up to n and what is the sum up to 2n, for example. It's very difficult to understand how they are located one compared with the other. So if we really want to see how they are, this is difficult. By the way, uniform distribution is something different because it is on average we want to know something. And this is third part. I'd say a word about uniform distribution mode 1. So this is what we know. There's something?
No, I was wondering why do you need non-negative?
Sorry?
Because you're using mod 1, huh?
Yes, you don't care, but then you have to say that, you see, the point is that if they are negative or non-negative, maybe you go from this one to this one and something like that. Oh, yes, because the sum is at least 1, so at least you can do that. Yeah, okay, fine. You're right. You're right. So if the sum is 1, you are sure to go among everything. Okay. In any case, what we are looking at are just non-negative elements, but okay, so maybe we go to something which is just to say that the sequence, I'm not going to tell you something about the sequence summation m up to n of phi m squared plus 1 over m squared plus 1, just to show that this is dense mode 1. Okay, maybe it makes sense to try to understand what is this sum. I don't know if for some students maybe it is not completely stupid to say what can be this sum. Why you have something which is linear and a nice sum. So what we have, and this will be also something. Summation when d divide m squared plus 1 of mu d over d. Okay, this is, if you have a sum, you prefer to write phi m over m as a sum of divisor, and then immediately what you are going to do is to reverse the summation, and so this will be the sum when d is at most x squared plus 1, because the divisor blah blah blah. And then you have some mu of d over d, this just going to depend on n, and then you have to say that m is at most n, and m squared plus 1 is congruent to 0 mod d. Okay? So now the point is to know how you can count the number of elements like that. Well, you have to know something about the number of solution of the congruence x squared plus 1 congruent to 0 mod d. So by the Chinese remainder theorem, it is enough to know it when you have something which are from powers, from primes and prime powers. Here you are not interested in prime powers because d, you know, is square free. If d is not square free, everything has no importance. So it is just multiplicative, so you have to know how many solutions you have mod p. And then this is quite easy. If p, since it is second degree equation, you have at most two solutions. Of course, if p is equal to 2, you have exactly 1. And otherwise, you have 2 or 0, according as p is congruent to 1 mod 4 or congruent to 3 mod 4. Okay, this is already due to Fermat, essentially, this thing. So, okay, so each time you have a solution, then you have to count the number of n which are congruent, the number of m which are congruent to this solution. Okay? So it will be something which is n over d. So if you count the solution, let us say rho d will be the number of solution of this. This will be something like d up to x squared plus 1 of mu of d over d, and then you have to count the number of solution, let us say rho of d, multiplicative function, which is 2 when p is congruent to blah, 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 blah. And then you have to count these things, and again you have some m over d, n over d. Okay, and when you are here, you are happy. You separate this, and you say this is this plus big O of 1, and this will be enough for what we want to do now. If you want to know for equidistribution, then you have to be careful about what is going on here. And just to say a word about equidistribution for this for m squared plus 1, then the problem is to know exactly that you have a good representation of the solution of those. And this is why you can say something on this error term. I'll make something easier than m squared plus 1 for the equidistribution, but you'll see that it's very important to know where you are located. If it is for something linear, it's much easier to know what are the solutions and how they are located, because this is just integral part. But okay. By the way, this is not true that it is integral part, because you don't know exactly where it is. This was not true. Integral part is not true, but this is correct. Yeah, because you may have, so you are sure that with the integral part you have this number of solution, but if it is a bit larger, there may be a few of them, but they are not more than one. This is 0 and 1. Okay, so now this is fine because you understand that what is the main term? Main term is n times something which is mu d over d square rho of d. Well, what is rho of d? You see, rho of d is something, for some prime it is 2 and otherwise it is 0, but it is at most 2 everywhere, so it is at most the number of divisor or something like that, so it is very small function, and so this is something which would be, and the average is 1, so this is something which tends to a constant and quickly, and you don't have to manage with the rest. And when you have the big O of 1, then it is again the same thing, because you have something which is essentially 1 over d. Okay, there will be some divisor function, so maybe this error term will not be just a log, but the power of a log. Okay? So then you will get a power of a log, and you are happy. Make it better if you think that on average this is 1. Okay. So this is linear, and you have a nice coefficient for that, and something which is, if you remember, we discussed about that, is the constant which is here irrational or not, and we don't know that. But if you want to ask question about whether it is close to be rational or not, please ask Shaoli and Purushottam. They are the experts here for those questions. And by the way, this is with the question with Enrique Ivanez about uniform distribution. We don't know whether this sequence is uniformly distributed or not. It is distributed if the coefficient, which is this sum up to infinity of this sum up to infinity, is rational. Then we don't know. If it is irrational, we know that it is equidistributed. You see, we are not in the situation if and only if, because there are so many error terms everywhere that it turns out that we can manage if it is irrational. Okay, the trigonometric sum are fine, but if not, we don't know whether it's true or not. Okay. So I want to say that this is dense. Okay. So I just give you some construction. How we can manage to prove that this is dense. Okay. So this is just in some way arithmetics now. So I give you some proposition. Maybe I start here. Maybe better to start here. In some way, all the arithmetic of m squared plus 1 is done. Now you can think that this is any polynomial. It will be about the same thing, except the construction will be. So what I'm going to tell you is, if I am looking at phi of m over m, it will be a bit simpler but almost trivial. If I look at a general polynomial, then it is even more complicated. So this is a mid-choice in some way to tell you how we can manage for that. So proposition, let H be given, which is at least 2. Let PH. So now this has nothing to do with the Lucas-Schinzel problem, what I'm writing. Just an arithmetic question, and then we'll see why it has something to do with this problem. A family of primes a family of set of primes pairwise disjoint. No prime belong to two families. Okay, all the primes that are involved in that occur at most once. Those occur exactly once. Congruent to 1 with 4 and larger than h squared plus 1. Okay, and we write pH to be the product of the prime P in pH of P. Okay? So what we say is that then there exist infinitely many integer n such that for every h less than h, 1, 2, 3, and so on, the integer n plus h squared plus 1 is divisible by h squared plus 1 times pH, and all its other prime factor What I mean by that is that all the prime factor which do not divide this, okay, are larger than n to 1 over 6h. So what I try to do.
So here I think this pH is product of I think 2h.
Sorry?
So this is notation. pH is product of primes in the.
pH is a family of prime.
Okay, so that is
and pH is the product of the prime in this family.
Okay.
Be careful, there's one is this and the other one is this. One is what is a dollar? No, is it? Yes. One is P and one is matcal P. Is it fine?
I think so.
Okay. So this is the set. The matcal P is the set and P is the product of the element. So how can you do that? Well, we heard in May about something which is called sieve. And this is what we are going to use. Okay? So proof, I am not going to give you a complete proof. I give you the construction for the proof and what you have to do. But okay, we let now. Okay, there's something I would like to say. Life would be nice if we could forget about it and say I take family of primes such that m plus 1 is divisible by some prime, and beside those one only large one. The same thing for m squared plus 2 and so on. But you see, when you are taking m squared plus 1 and then you are taking m squared plus 2, at least you cannot do only with any prime you wish, because one of those two, m plus 1 squared plus 1, at least one of those two will be even. So you have to take care of all the prime up to h, or all the primes up to h squared plus 1. Then you will have the larger one. But the small one, you have to say, okay, we cannot cheat with them. We have to take them into consideration. This is why you have this small thing, which makes your life a bit difficult, but I mean it's a matter of fact, and you can manage with that. But you cannot forget about that. If this were not here, life would be just easy. Okay? But we have to do that because one of them will be divisible by 2, and then one of them will be divisible by 5, and so on. So you have to take all these primes congruent to 1 mod 4. Okay. So the proof is essentially a construction, and I will tell you what is there, and possibly this will be enough. So we construct D, which is the product h is 1 to capital H of h squared plus 1. There's all the little things which are bothering you. If we were not taking with the squares, then it would be just the product of all the integers, and it will be something which is n factorial, h factorial. So thinks it is at h factorial, but the one which is adapted to your thing. So you think if you have another polynomial, it may be a bit complicated. So well, I write P to be the product of the pH. That is to say, P is the product of all the prime which are in my family. My family is given. Simply know that they are large prime, blah, 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 and so on, something like that. And also something which will be interesting is another element which is K, which is the product of the prime up to 2H, and P does not divide D. Now, not in this family. You have also to consider this, and Q is D square K. Fine. I mean, this is just construction. Okay. Maybe I can start like that. Yes. So if the life were easy, I would do the following. I would try to say I want m plus 1 to be divisible exactly by n plus 1. I wish them n to be divisible by P1, blah, 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 n plus h to be divisible by pH. And then I would like to say that all the other factors, there are no other factors than that. Okay? So what I would like to try to do is to take, let us consider this product. This product, it is a polynomial. You may have fixed divisors in it. See what are the fixed divisors. And if you have no fixed divisor, then you are happy, because Sieve will tell you that you may find n so that there is no other factor than very large ones. I mean very large, those factors. Okay? Yes, but the point is to try to find, this will not work like that. So you have to be a bit more crook, and this is what I try to tell you how we can do that. So what we do is the following. For convenient, I will say what is for a convenient R. We have to show that there exists some convenient R. A convenient R we let fh of x is a polynomial in x, which is q px plus r plus h, and this is square plus 1. So what I would like to do is to have something like that, and then I consider the product f of x to be the product h1 to capital H of fh of x. I mean, this I can do for the time being for any r. For any r, I can consider this polynomial. You see, what if I am going to take one value of x, then this is essentially something which is m plus 1 square plus 1, m plus 2 square plus 1, and so on, so that this will be consecutive values. So what I would like to say is that in this number there is no fixed prime divisor, and so all the factors are large. So this is why we are now trying to work to say that the fixed divisors, we know exactly what they are. They will not be that complicated. And beside those fixed divisors, there is no other fixed divisor. So we have to work on this R. What can be this R? Okay. So for each P in P, there exists xp such that xp square plus 1 congruent to 0 mod p. We did that because p is simply congruent to 1 mod 4. Okay, so you can find what is xp. You take one of them.
Yeah, so that P means the union of all the primes in the family. Okay?
Yes. This is defined. You are right. Matcal P was not defined, but this is defined. Okay. Okay. So for each P there, you have a solution like that, and we let R such that QR plus H, Q times R plus H no, what does that mean? No. Such that for each, let R such that for each, P in pH, we have Q R plus H is congruent to XP mod P. You see, in Q, you have only small primes, and in P, we ask to have already large primes. They are larger than 4 times h squared or something like that. So they are large primes, so this one is congruent, is coprime with P. Okay, so you have solution of this, since this is congruent. So you have R, which satisfies all this, but all P, and so there is one R, which is okay mod, which will satisfy all those congruencies for all H. Okay, they are all distinct, pairwise distinct, so you are happy with that. So this is the Chinese theorem. So okay, so for this is the R we have, and now for this, the question is just to show that what we have to prove is that, or to prove, I will let you assume that this works for all H and all N. We have the GCD of FH of N, and QP is H squared plus 1, which is just the factor we were interested in. We made this on purpose, and the fixed divisor of F is exactly dP. And this is not completely trivial. You have really to work on that, and the point is, but when you have the construction, it's fine. Okay? And so now you apply the sieve. So this is you have to prove. Okay? This is not difficult. This is more difficult. It's just arithmetic. For our construction, lead that you have this. Okay?
What is the fixed F? What is the last fixed F?
The fix of the polynomial F,
Okay.
which is this. The fixed divisor. Fixed divisor is the divisor, is the GCD of all the values of a polynomial. Okay? It's the GCD of all the values of this divisor. So you can divide it by this divisor, and you have something which is with the integral valued. And then if it is coprime, it makes sense to say if this polynomial has no fixed divisor, then of course what you see, Schinzel hypothesis, we were talking about Dixon hypothesis for linear polynomial. Schinzel hypothesis would tell you that all of them can be prime. Well, okay, we don't say that they are prime, but at least the sieve tells you they have no large divisor. You can kill out all the small divisors. Not enough to say that all are primes, but at least you kill all the small divisors. Okay, and this is the point which is important, and then you apply sieve and you have the proposition. Okay, so here you have some arithmetic work. There is no point to do that on the board. I mean, it's written. You have the paper, and then you apply sieve, and sieve tells you, okay, we have all the things. So now, what I erased the proposition, which is maybe not that great, but what I want to do now is to show that indeed the sequence phi of m square, the sum of the phi over m square over m square is dense. Okay? So this was not clever to erase the proposition. Can I do that?
But you don't have enough board space.
Yeah, okay. So you remember what we had is some family of pH, which have to be large, congruent to 1 mod 4. This is what we wanted, and So we have this family, and then we said that n plus h square plus 1 is h square plus 1 times ph times large large primes. Okay? Larger than n to the 1 over 6m or something, 6h or something like that. Okay, this is what was the proposition. So, okay, I'm a bit fed up by writing phi of m square plus 1 divided by m square plus 1, this is Cm. Okay? So, of course, what we want to do is to apply the initial lemma to say that by a good construction, all that is at our disposal. We can choose them exactly as we wish. So what I want is to say that construct the Cm such that the Cm are small and the sum of the Cm is larger than 1, because this will be just the difference between the elements. So what we want to have is to show that we can find Cm is less than epsilon, find Cm plus h less than epsilon, and sum of the Cm plus h larger than 1. Okay? So, the fact that the Cm will be small, we'll get it from the pH. The large prime, you see, contribution of large primes will not be great because it will be a product of 1 minus 1 over p, and if p is very large, this is very close to 1. There's nothing to do. So what you can play with to do something which is small is on this part to say I want pH to be just something between epsilon and 2 epsilon or whatever you wish. Okay? So this, there will be in the phi, there will be phi of h1 of h square plus 1 divided by h square plus 1, and this you cannot do anything. This may be very small. Okay? But at least it's fixed, you know what it is. We'll see what it gives at the very end. So we are just going to play with this part. So you know what you have? You have primes which are large primes congruent to 1 mod 4. And this will be just the product, the contribution to Cm of this will be the product when P belongs to pH of 1 minus 1 over P. Now, if you remember, those are, you have a large choice. The only thing which is said is that they have to be large. Good. You start with pH, h is equal to 1. They have to be large, and they have to be congruent to 1 mod 4. But if you remember, we were proving, the way Dirichlet was proving the distribution of the primes between 1 and 3 mod 4. It was indeed proving that the sum of the inverse of 1 over p when p is congruent to 1 mod 4 is divergent. The same thing for p larger than 3, congruent to 3 mod 4. So since this is divergent, you can find this and tends to, those elements tends to 1, you can prove it exactly where you wish. So you can find primes such that this belongs to epsilon to epsilon. Epsilon given small. Of course, don't take me 10, this will not work, but take something which is small enough.
This capital H is also.
Sorry?
The capital H, that is big, or because epsilon times H has to be bigger than 1.
Yeah, of course. Yeah, then we need H to be rather large. But for the time being, We say if I give epsilon and h, we'll see what will be the relation between them. But for h and epsilon, I can construct something like that. And it will be a set of pH satisfying what I need.
Probably to be consistent to your main theorem, you should take epsilon by 2 comma epsilon because you want the number to be less than epsilon.
I want it to be less than epsilon.
Yes.
Okay, then let us take epsilon over 2 and epsilon. Okay, good. Okay, now when I want to go to the next h, of course I have at my disposal, I cannot use the one which I have here, but there are enough because the series is convergent, is divergent. The product is convergent to 0. So I can find it for any h. This is not a problem. I can find pH that I have all that. Okay? So this is fine. So it tells me that this is something which is known. The large prime are something which have a contribution which is peanut. They are really very large. This is 1 minus, you see, you have something which is 1 minus 1 over n to the 1 over 6h. And this will essentially be 1. If n is sufficiently large, this is just nothing. Okay, so now this is fine. And then what you have to say, oh, I did that with this, but I did that in another way, but it's not a problem. What I want to say now is that what is the sum of all this contribution? So what I have to say is what is the sum when h is from 1 to h of all this Cm plus h. So what will be the contribution? There will be something which is phi of h squared plus 1 divided by h squared plus 1. Okay? Then there will be something which is the contribution of the pH. The element of the pH will tell me something which is in some coefficient which is in epsilon to epsilon. And then there will be the contribution of the last one, and this is whatever you wish, 1 minus epsilon over 20 or whatever you wish. Okay? Larger than 1 epsilon over 20 and even tending to 0. So when you sum all that, well, this is fine. This is something which is at most epsilon. But when you sum this is something which is fixed. So this goes out in some way, and this is something which is fixed and which is about a constant times h. So if h is sufficiently large, this will be larger than 1. Essentially, h has to be something like 1 over epsilon, a bit more than 1 over epsilon, because this constant will be small. But okay, and so you are done with this, and everything is fine. So the real part is really the arithmetic to, if you want to prove it, to prove what is the fixed divisor of this, and if you want to build that, is just to construct this. I don't say this is the best way to do it. In any case, it works. Okay, fine. So, and essentially all the things are density are with this type of condition. Even if you take the arithmetic means of phi of m over m, it will be something of the same kind. Now we are going to uniform distribution mode 1. Then we're happy because uniform distribution mode 1. So we have many more principles. 24, it's fine. Some principle. And we have a lot of possibilities to play with. So one which is clear is that UN, I don't repeat all the time that UN is a sequence of real numbers. UN and UN plus little o of 1 are simultaneously UD1 or not. This is clear. You are in an interval, and you are in an interval which is slightly a bit larger by epsilon, or a bit smaller, and you count the number of times and you have everything you wish. Or you do that also by using Weil criterion. Everything works. Bare hands are Weil criterion. Okay, you have also something, if you shift by a fixed element, it is also the same thing. You have also something which is interesting, and UN plus kappa is fixed, log n, are also simultaneously uniformly distributed mod 1 or not. Moving it by k log n, because k log n is going very slowly. You have to work a bit, it's a nice thing. This is used in the uniform distribution of the geometric means. We have something which will be this with a coefficient n plus something, a constant time log n, but this is fine. It is the same thing at the constant wave at the beginning. Okay, also something, yes, this, maybe I just go to this one, which is the one will be relevant. I don't want to give you everything. Okay, let a sequence epsilon such that summation n of 2x of epsilon n is little o of x then un and un plus epsilon n are simultaneously UD1 or not. So the point is the following, that there may be some really large values of epsilon n, but if you have some large values of epsilon n, they don't occur very often. Large values, larger than some epsilon given epsilon, large values are on a set of density 0. But if you modify a sequence UN on a set of density 0, then it is the same thing, because when you are just counting the number of elements in an interval, well, maybe you drop something which is a little o of x, it has no importance. The frequency with which it falls into your interval is the same. So large values of epsilon n are not important, and then for small values of epsilon n, then you will be happy, because it is just this essentially. Okay, you have to take some limits, but this is very convenient. Okay, so possibly I'll just go now to the Bn.
So here in the first question, like for example, if I take this, suppose UN mod 1, there's something now you choose of 1 to be.
Sorry?
Like in the first one,
yeah.
UN and UN plus of 1.
Yeah.
If you take of 1 to be something which is very like, so UN modulo 1 plus that thing to make it 1 or 0.
Yes.
Something like so. Then.
No, but you see, what I want to say, that they are uniformly distributed mod 1. I don't say anything about if they are. You see, the point is that fractional part of UN is the same thing if it is uniformly distributed mod 1. Fractional part of UN is the same thing as fractional part of UN plus little o of 1, almost always. Okay? Because you have nobody which is close to, which is in a small interval. No, it may turn out that as regards the values of, I don't say that fractional part, I don't say that un is always equal to un plus little o of 1. Okay? This is not true.
Okay.
But what I say is that this, if one is uniformly distributed in mod 1, then you are not changing much. Okay? And if you are changing much, it means that you are not uniformly distributed in mod 1. And you have no, this is fine. Okay, so let us go to our business. Bn is equal to sum of phi of m over m. M up to n is uniformly distributed in mod 1. We keep that in mind because we are going to use that. Okay, it is, we may write this, we should usually use this. We are going to use something which is a bit more symmetric. By the way, someone was saying, what about the distance of x to the nearest integer? Is it possible to do something like that instead of the fractional part? This will go also. And even this is better to write it that way, plus x minus 1/2. And this is a nice function which we'll call psi of x. And you see what is psi of x? Psi of x is of course something which is periodic, mod 1. If you start with 0, you have the value minus 1/2. And then here you have the value 1/2. And so it is a nice symmetric function. If you have x which is an integer, what is it? If phi of an integer is minus 1/2. So the value here is minus 1/2, and then it will stop, and it will start again at minus 1/2. This is not very nice. It may be better to modify it a little while. So this is not really bad. Phi x will take the value 0 here. Okay, you just modify it at the integers. It doesn't make a big difference. What is interesting is that if I want to write it, it will be more correct. If I write it with that, this is minus 1/2 sum from k different from 0 of 1 over 2 pi I k times exponential, you know what is psi, times exponential is a Fourier expansion, exponential of 2 pi I kx. And this sum converges if you are clever, that is to say, if you take the summation in a symmetric way. You take all the k which are an absolute value less than k, and then when k is tending to infinity, this series converge, and it converges towards exactly this function, the psi star. So that if it is different from 0, which will be the case almost always from what we are looking at, then star, not star, you don't care much. And you see, it's almost convergent, except that it is 1 over k. Of course, it cannot be absolutely convergent. If it were absolutely convergent, this function would be continuous. So it's not exactly the case, but it's not far from being continuous. So this is nice. So okay, let us write now what is Bn. So I go a bit quicker. I don't write, you see, all the summation with mu of d over d, and you reverse the summation, and you have all the business, and you have something which will be n summation of d less than n of mu d over d square minus summation d is less than n of mu d over d psi n over d plus 1/2 of summation of mu d over d, where d is up to n. You see, I didn't say that this was big O of 1. This is what we were doing to say that the other term is something like a log, but of course we want to take care of that. It is very important to know what can we say about this. So this is not important. In some way, this will be n times, as soon as you know that the sum, you have to know something. You have to know that if you write m of x to be the summation of mu of n up to x, you have to know something, that this is something which is at most x, x is trivial, that it is little o of x is equivalent to the prime number theorem, and you can prove that it is something like some power of x. You may win any power of x, of log. Okay? Even winning 1 or 2 will be enough for what we want. So this means that this is just peanut. This is a little o of 1. There's no problem with that. And this is a constant time little o of 1. So what is really the point is to work about that. So what do we have to understand that this is not little o of 1. Definitely this is not little o of 1. What are you are worried about something? No, it's fine. What is really the point is to know what is going on here. And if you compute what it is, definitely this has some importance. It's not little o of 1, so you have to try to understand how it goes. And you see, if you make some computation that Hassani did, you see that it has something which is more or less periodic in n. And indeed, what you can prove, and this is all the problem, is to prove that this is the summation of d divides product of p up to z. So you are taking only the number n, which are dividing a small number. Okay, so z is something which will be more or less connected with n, but if you take n between capital N and 2 capital N, then it will be the same value of z. Okay, if you have something, and you try to get it larger, of mu of d over d, psi of n over d, and then there is some error term. And then you have some error term, and this error term depends on n and z. Okay. So one thing you have to work on, is equal. I have to say that this is your 6 over pi square n minus something like that. But this is a good guy. You're not afraid by this one. Now you are lost here, and here you have to be somewhat careful. And it turns out that what you can prove on this, at some cases it can be rather large, but what you can prove is that the sum, when n is up to x, of e of nx, nz, is something which is, you have some condition to have, but not too much, z2 minus 1/2. So now you have 2 points. How do you do for getting this? So you know that here you have the sum up to all the n, and here you are just a sum over the element with small prime factors. So you have to write down what is the difference, and this difference will carry some psi function, and you need to know something about only what is the error term on average. By the way, the error term on average is very nice, because this is exactly what you have here. If you know that you have something on average, it's fine. But this is not very nice to have this on average. So what you do is to square it. Well, if it is with the square, it is small, then it is small also for the L1 norm. Just apply Cauchy. Okay? You apply Cauchy. If you win something of one of the terms, by Cauchy, you know the other one you are not going to win anything. It is 1 times this square, but it's fine. You will have something. This is, by the way, why there is one half here. For the square, you will win something which is 1 over z. And when you square it, then it's fine, because what you do is you have some sum which is here, and so you can open the sum, and then you have some arithmetic to do with all the elements k, and so there is still again this mess to work. So this is the most important, is to work with that when you open the sum. Okay.
Is that something like a power of log x?
There may be a power. I mean, I am even cheating. I'm even cheating, because to allow that, what you have to do is first to say, no, I am just interested in the d which are at most capital D, and capital B will be very close to n. So I am so cheating that cheating by a log has no importance now. But essentially, this is what you will get if z is sufficiently large. So now you are left with this. What can you do with that? There's something very nice. This is a periodic function. This function is periodic with period, the product, this product, because you see, each time d is always a divisor of that. If you take something which is n plus a multiple of that, it will be the same thing, because there will be some integer, and this is periodic with period 1. So in n, whatever the d which divides this, it is a periodic function. And definitely, if you look at what is Bn, you see this periodicity of Bn. This is periodic. Well, now it's fine. You have something periodic. I didn't put it here because I was looking at the watch. But you have also the fact that if you have something which is periodic, then if all of them are uniformly distributed, then the large one is also. I mean, if you have a union, you separate your sequence into 2 sequences, and then if you know how to do for 2, you know how to do for more. If each one is uniformly distributed mod 1, then the union is also distributed mod 1. So then each one will be distributed mod 1, because now this becomes constant, and you still have this 6 over pi square, which is irrational. So all of them are rational. Since this is periodic, this is also uniformly distributed. You just have to play a bit with that. And finally, your business is also equidistributed mod 1. Okay? So it's hand waving, but it may help you. I hope that this hand waving helps you reading the paper if you want to read it. This is the only thing I can do in some way. But okay, fine. Still have 1 minute and a half, no? Yeah, 1 minute and a half. There is the question about g of n. Gn, about you can do the same thing for the uniform distribution. And then you have the question of 1 e product when over the p, at least 2 of 1 minus 1 over p to the 1 over p. I think it is something like that. What is this constant? Well, this constant we don't know. We were with Henrik in Princeton when we were looking at that, and Richard Bambi was kind enough to make some computation to say if this is a rational number, its denominator is at least 10 to the 20. So it's possible that it is irrational, but we don't know whether it is irrational or not. And here we are lucky because this is if and only if for Gn. Gn is sufficiently smart that we have something which is if and only if. So we know that Gn is uniformly distributed mod 1 if and only if this constant is irrational or not. Okay, we are really close to 45 now. Okay, fine. So